Hi, Mcebo here. In this video, we'll be discussing how best we can apply the information unit structure concept in discussing or understanding complex numbers. So we'll be using this Wikipedia article as our example. In this video, we'll only discuss the definition and the notation section. As expected, the author started his discussion with the definition of complex numbers. So we start based on the concept of real numbers. A complex number is a number of the form a plus bi, where a and b are real numbers, and I is an indeterminate satisfying I squared is equals to -1. So basically this is trying to describe the entity which is a complex number in this case. So we are going to give it a blue color. We are given the form that it's of the form a plus bi. This way, a complex number is defined as a polynomial with real coefficients in a single indeterminate I for which the relation I is imposed. It's also a description of the entity, but they're introducing it as a polynomial now. Possibilities of it being a polynomial. Based on this definition, a complex numbers can be added, multiplied. This is an action. This is what is possible. This is what you can be able to do with complex numbers. You can add, you can subtract, you can multiply, you can divide. So the author is kind of ahead of himself. So let's put it as an action. Let's give it yellow. The relation a squared plus 1 is equals to 0 introduces the equalities I to the power 4k is equals to 1, and so on. Is induction, which hold for the integers k. This allows for the reduction of a polynomial that results from the addition and multiplication. Okay, this is a result of what this can do. This induction trick, they are saying, it helps when you want to reduce any polynomial that results from addition. So this part is an action, but this one is a result of what this can do. So let's put the first part as an action, this part, but the rest of this paragraph, it's a result. The real number a is called real number of the complex number a plus b. The real number b is called the imaginary part. So we are still being introduced to these types of numbers. We are told that there is this part which is the real part, the other part is called the imaginary part. So it's still let's give it blue. It's still a description of the entity. Formally, the complex numbers are defined as the quotient ring of polynomial ring indeterminate I by the ideal generated by. This is still a description of the entity. A real number can be regarded as a complex number a plus 0i whose imaginary part is 0. A purely imaginary number bi is a complex number 0 plus bi whose real part is 0. As with polynomials, it is common to write, so this is just simple multiplication. Whatever you multiply by 0, it will turn out to be 0. So this concept also applies to to complex numbers. That is what we are told here. That's what we are introduced to, which is not new. So it's also a description of how these number systems behave. Since in polynomials with real coefficients, the multiplication of the indeterminate I and the real is commutative, a plus b may be written as a plus bi may be written as a plus ib. This is often expedient. It's commutative. That's what they're trying to explain here. You can either write it as bi or ib, so it's still the same thing. So it's another behavior that also applies in other types of number systems. You can write ib or bi, still the same thing. It's still the same thing. The real part of a complex number z is denoted by RE in bracket z or this. So that's how you can represent the real part, and this is how you can represent the imaginary part. Meaning, if you find something like this RE in brackets, the complex number, they are looking for this real part. They want this part. If you find IM, which is imaginary, they are looking for this part without the I. They are looking for the 3. So it's still the way this number behave. They're still describing the number, the complex number. So we'll give it blue again. The set of complex numbers is denoted by C. Okay, it's just a set. We are told that its set is C. In some disciplines, in particular electromagnetism and electrical engineering, J is used instead of I, since I is frequently used to represent electric current. In these cases, complex numbers are written in the form A plus BJ instead of I. So they're still just introducing the numbers to us. At times it can be written as J. That's what they are saying. It's not I all the time. So now we have finished reading this section. The next part is to write notes. Is to use what we have read to write structured notes. We are done with the notes now. So we have got them well structured. Here we've got the setting. We don't know the setting yet. The part we have read was not clear about the setting, so we just left it like this. Then we've got the entity. We know we are dealing with complex numbers, and then the description of the entity. That's why all of this is blue. Then now below we've got the actions and the results, the actions and the results. So this is our notes. Then from our notes we derived the notes. So from that chunk we've got only this small portion and it carries everything. If you are in mathematics, you will understand that this is all there is to it. This is a polynomial. The A part is the real part. The B part is the imaginary part. That's all there is to complex numbers. And then the actions, it can either be multiplication, it can be addition. Then the induction they showed also has a result, which is that it can be used to reduce polynomials easily without going through all the steps. So basically, this is the notes. These are the notes. This is the note structure for the first section. That's how simplified now that big chunk of text. So thanks for watching. Don't forget to like and share the video and then subscribe. Thank you.